Okay. Good afternoon, one and all. Welcome to another session of Creative Online Weekend Talks of episode 142. Creative is a group of people who are eager to gain new knowledge, and sharing of knowledge increases our knowledge is our tagline. Vision of Creative is to build constructive thinking on various domains. As the clock strikes 3 p.m., our virtual stage comes alive, and live streaming on Creative GVD YouTube channel. And today's focus on celestial marvel that holds a special place in all our lives, the sun, as our nearest star. It's a source of endless fascination and mystery. Throughout history, humans have looked to the sun for guidance, inspiration, and understanding. And today, with the help of our esteemed guest, Dr. Srijit, sir, we are illuminating journey into the heart of this radiant celestial body. Before start, I extend a warm welcome to all of here who are joined here, and I welcome today's speaker, Srijit sir, for today's session. And I call Raghavi, Creative Volunteer, to introduce today's speaker. Over to Raghavi.
Good afternoon, everyone. Myself, Raghavi, Creative Volunteer, studying in 8th Samita Academy in Bangalore. I am here to introduce today's creative resource person, Dr. Srijit. Dr. Srijit did his bachelor's degree in physics for Calicut University, Kerala, and master's in physics for IIT Madras, Chennai. Later, he joined the Space Astronomy Group of U.R. Rao Satellite Center, ISRO, Bangalore, as Junior Research Fellow. During this period, he worked on India's first dedicated astronomy satellite, AstroSat. He completed his PhD for the same group in the field of solar physics, which is studying the physics of sun. After PhD, he joined Trinity College, Dublin, Ireland, as a postdoctoral research associate. In 2017, he joined the Inter-University Center for Astronomy and Astrophysics, Pune, as a research associate. From 2020-21 onwards, he is working as an assistant professor at the Manipal Center for Natural Sciences, Manipal Academy of Higher Education. He is also the project scientist from 2018 onwards to present in the team that developed the Solar Ultraviolet Imaging Telescope on board the Aditya L1 mission. Dr. Srijit's research interests are astrophysics, solar physics, and space science instrument development. Join me in welcoming Dr. Srijit for today's talk, and thank you, Creative, for giving this opportunity.
Over to you, sir. Thank you, Raghavi. Over to you, sir.
Good afternoon, everyone. Hope I'm audible and clear.
Yes, sir. Yes, sir.
Thank you to the team Creative and for inviting me here for this session. And since I'm not very clear or sure about the audience, I was told that this is a range of audience starting from students to professional researchers. And so I'm not very sure whether my level of presentation will make everyone happy. Some of you might get bored, some of you might may find too easy, some of you might find it too tough. So please feel free to ask me in between. Don't hesitate to stop me in between and ask any questions. Because if you keep it towards end, you may forget your question by the time you reach end. So I'm okay to getting interrupted whenever possible. And especially in this virtual platform, it's very difficult I cannot see you people. I'm just staring at my computer screen. So I really don't know if somebody is raising their eyebrows, because in the normal audience, when we see the people, I can make a guess that people are not very happy with my explanation or such things. So I can try to go more detail and explain. Here, since that's not possible, you have to interrupt yourself by unmuting your mic and making your noise heard. Okay, so what I'll do is I'll just give a brief idea about the sun, our nearest star, and about the Aditya L1 satellite, which was a recent mission. Actually, I was supposed to give this talk on Aditya L1 in last September when Aditya was launched, but due to some other hectic activities that never happened. So since now I thought I'll give a brief idea about sun first, and towards the end we will just talk about Aditya L1 as well. Okay, so again, one more caveat or one more excuse or apologies is that I cannot cover everything related to the sun in this 45 minutes. In fact, that's some sort of short-term course on everything on the sun. So I'll just give you a brief touch-up on sun and something interesting which maybe some of you would like to get interested in the field of solar physics. That's what my plan is. Okay, so in the introduction, Supriya told that sun has enthused and given direction to the human beings from time immemorial, which is very true. If you think of the human curiosity, when the human beings started becoming curious about anything in science, definitely it would have been sky would have been played a major role, because think of human beings as hunter dwellers in a forest. Our great forefathers, they were just living in caves in a forest with hunting and living like that, like a nomads without settling down in one place. Even then, even of those times, maybe 50,000 years before or 1 lakh years before, even then, they would have noticed these things on the sky, this blinking, the twinkling diamonds on the sky, which comes up during night, and then very hot burning stuff like a ball of fire coming up in the daytime, and this periodicity continuing over time and again, the day, the night, the day, the night, the beautiful sky and the blue sky, etc., etc. So definitely that would have invoked their curiosity, and they started observing it very carefully. They started seeing a pattern in this. They started marking this pattern on the cave walls. Even now, if you go to different caves, you still see those markings of ancient Homo sapiens, or even before that, or about the calendar system. What we call today the calendars was born by the human being's curiosity of this pattern of night and day. So people are, of course, so hence we say that astronomy was one of the earliest science where people started methodologically studying a pattern that they observe in the nature. Of course, in that, as the people curiosity improved, they started using instruments, telescopes, and other things to observe the sun. So there is a question which people ask me often when I tell this, that this has been observed for so long, and what is motivating you even today? Is it not getting bored? Because we do these skywatch sessions many times. So initial few times it is very interesting for kids. After a few times they started saying, oh, it's the same sky we are seeing. I have seen all these already in previous skywatch. What is interesting which is make you motivated to do a research in astrophysics? What makes us motivated is something like this. So what you see on the left side is an image which you can see with your eye, or you can take with your normal camera from or naked eye object, where there is a star forming region. There's a nebula. Lot of stars are there. Small young stars are there, and there is some hazy thing which has been seen by human beings for many years. What you see on the right is an image from Hubble telescope. When Hubble took a photo of the same region, you see it's a totally different thing. Both are real photos. Okay. So what you see here on the right, if you can see my pointer, let me try to make it a pointer. You can see here, this is really different from this, right? So this was seen maybe 20 years before. And of course, people get curious that, see, what is this? What is this? Is the same region? Then what are all this colorful stuff here? Is it dust? Is it gas? Is it something else? Etc. etc. So that makes us more motivated. Though this region has been studied for 50,000 or 1 lakh years, people have been seeing this region. When we started taking images with new instruments, better instruments, you start getting more and more curious and interested in this, studying it more. That's a fundamental thing makes astronomy alive. That every day you start getting new information. Maybe it's the same sky, but we start getting more and more information, and that makes us more and more motivated. So universe is very big. I'm not going to cover everything. You might have seen these things. We are a very small part of the universe. Out of very big universe, Milky Way itself is a very small galaxy, and we are a very normal star in the Milky Way. So what I will be discussing today is only about one star in this whole billions and billions of stars in the universe, which is the sun. So I will be talking next 40 minutes only on the sun, nothing else. I think each star you can talk about years, months and months continuously. And as Supriya started in the beginning, sun has been there in our civilization from very beginning. As I told, because it has been motivating or in generating curiosity, and people knew that sun is somehow connected with climate, their livelihood. For a plant to make a fruit to ripen, you need, for a plant to grow, you need sun. It is part of our civilization. You go to any civilization in the world, you will see sun god as one of their major gods in all civilization. If you look at sun is a normal star, which is not any special, because many of the astronomers who study will be studying about exotic objects, or like you would have heard about black holes and neutron stars and supernovae and whatnot. These are all compact objects, what they generally call, on activities happening. This is when a star is dying most of the time. That's a very special case, like, or very interesting thing, that when a star is dying, what happens? There are people who study about star formation regions and nebulas and all those things, clusters and all those. It's a very interesting region. Whereas sun doesn't fall in both of those. Sun is a normal middle-aged star, sort of boring time of life. And it's not a special star that way, if you look at the thing. But still, people are interested in sun because it's very special for us, because it is our star, sort of, right? That's why I told sun the star in our neighborhood, because it's the only star where we can resolve. Resolve means you can see it in detail. You know, right? When you have a bus coming from far away, you cannot resolve the letters on the board. So you don't know where the bus is going. As it comes close by, you can start able to read what is written on the bus board. Means you are able to resolve it. So you can see in detail. Otherwise, it is just an object. So most of the stars what we study today are just an object, just a twinkling point. Whereas sun is something which you can resolve, and you can see the surface, what is happening on the surface, activities on the surface. And we generally compare those with other stars. So this is the only star where you can see this in detail, special case where many of the fundamental physics processes take place. And of course, it is our star where all the solar system planets are linked to, anchored at, and hence it's very special. It also is very special because it provides almost all the energy for our livelihood. Not about solar panel energy I'm talking about. When I say energy, don't think that solar energy is about just keeping solar panel and doing. Just, you see, think of in another way. Even if you think of the electricity which is coming here, which is produced maybe from a dam. It may be from a dam here in near the Jog Falls, or it may be from somewhere else. That water reached that dam to this high potential region because of the sun, actually, right? Because of the sun evaporating the sea, and the clouds moved, and it rained on the hills, That's how the water in the sea reached the hilltops. That is why we could stop it and convert that potential energy into electricity, right? So even the tidal power or any other energy production you think of, it is somehow connected to the sun. You may ask me nuclear energy whether it is connected to the sun. Of course, that's a different topic to be discussed, but definitely it is connected because finally we are all taught to be came out from the same cloud, because both sun and earth would have been created from the same cloud of hydrogen, hopefully, or same cloud of some dead star. It's a different topic. We don't want to digress much, but it's very interesting, both philosophically and scientifically, to think about both sun and earth came from same collection of gas, which is of course a dead star because we have iron, right? Okay, it's a different thing. Also, sun is very special because it's a unique laboratory where you can learn many other things like fusion, for example, just for example, or many of the spectroscopical things, because there are many forbidden spectral lines you observe on the sun. Very difficult to create on the lab. If you want to study many of those spectroscopic things, or even polarimetric things, or even how the light and plasma, how the photons and plasma interact, how the magnetic field and plasma interact, apart from fusion, there are many fundamental physics process which very difficult to generate in our lab. So what you do is you look towards the stars of the sky and try to observe them. Since stars are all other stars other than sun are very far away, sun is the best subject to study these details of many of these physical processes. And you all know that core of the sun, there is nuclear fusion happening, where protons joins together and produce higher nucleus. During this process, it releases lots of light, and this light, they come out like a lot of energy is gone out. So these are it's like nuclear blast bombs, like lakhs and lakhs of nuclear bombs going off at a time. That's what is happening in the sun. And the energy comes out in the process of radiation initially. Then it does something called convection. We will discuss in a moment. And then it again, part of radiation, it goes out from the surface of the sun. There is a question here asking why, as you see, the proof of convection is a real movie of what is happening on the sun. So just to show that the boiling of the sun is a real movie. Let me see whether I can see this. Okay, so okay, so okay, yeah. So you can see this boiling of the sun surface. This is what the convection is. In the previous slide, I showed that there is some energy mechanism here called convection. You can see it is convecting. It's a proof of that the sun surface is boiling. It's very interesting actually. So when if you take a small region and carefully observe, you see that the hot gas comes out as a part of the fusion, heats the gas, and the cooler gases start flowing down. So this is called the rolling convection, very standard thing. Like when you make tea, if you go to your kitchen and make tea, you see a similar thing, sort of convection there. Since the water is not dense like these things, you may not see such cells clearly, but if you take some denser material like oil and all, you can even create such things in labs. People have done that, such convective cells. But this you see, the hot gas will come out and the cool gas going down is something which you see everywhere. So now the question is, why is this sun very stable? Because we see this big blast happening and still the sun is very stable. The reason is this fusion is making things move out like there's a strong force outward because of this nuclear fusion happening inside. This strong force outward is balanced by the gravity. Gravity is the pull of material towards the center of gravity of the ball or any object. So all this material which has been pushed out is also pulled back by the gravity. So what you see is this is little uh, uh, sun don't move like this. You see is there is a force. This is just to show the force. There is a force outward and there is a force inward from because of the gravity. In reality, what happens is two forces work on this surface of the sun across the sun, all the plasma on the sun. There is outward pressure and there is inward gravity. This leads to lot of waves on the sun. You see so many types of waves on the sun. There are pressure modes, there is gravitational modes, there are different modes of these are real data. You see the sun surface is having lots of waves. People call it G mode, P mode, etc. There is a 1 minute mode, 3 minute mode, and all. Technically, the sun makes sound in that way because these have waves. When it makes pressure waves, whatever you call sound is nothing but pressure waves, right? So there are some WhatsApp forwards going around saying that sun makes sound, though the sound in that WhatsApp forwards are not the right sound, but sun makes some sound, and the real sound of sun is like a 1 minute oscillation is like it's like those Akashvani sound when there is no station. You would have heard, no? It's like some raining sound or some just a blank sound. There is nothing beautiful music or anything coming out of that. Okay, so if you look at how the sun inside is, there is this core where all the fusion happens. Then there is this radiative zone. What happens is this gamma rays or the energy produced in the form of gamma rays, they make sort of a random walk outward. And they take millions of years to come out of this surface, from core to surface. Reason is it's so dense. So every gamma ray goes and hits, scatters and goes, then it again gets scattered, and it takes a lot of time to reach here. Actually, the light what you see right now, that energy was produced actually many years before, lakhs of years before. That's when that energy was produced, what is reaching us now. And at some point, it becomes so tiny and it loses its energy during every scattering. And at some point, it comes to a ultraviolet regime, the energy of the thing. And that is when the temperature is also in a way that molecular formation would have happened. And this layer absorb all that energy. And when they absorb the energy, it goes to a convective way of transferring heat, just like how as I told, water boil. The water at the bottom absorb the heat from the utensils which you have kept using, and then they move up, right? That's how exactly it happens here. This absorbs and it starts making a convective boiling motion here. You can see the convective cells here. And they reach here. And once they reach here, again, they start emitting like a black body. But the important thing is that because there is an absorption and re-emission happening here, you lose all the information about inside. All the information is lost because the rays coming from here is absorbed and then re-emitted. So what you see is only the re-emitted surface. So it becomes like a black body. Exactly like when we say water is boiling or when you're making tea, you don't see the stove, right? Or the flame. If you look from top, for example, if you're looking from top, you don't see the stove flame because the flame is absorbed by this utensil which you are using, the kettle you are using, and it has been re-emitting. So what you see is a bright kettle. You don't see the flame, right? Similar way, of course, it's not a perfect black body or anything, but similar way, I'm just saying an example. Sun is also, of course, not a perfect black body, but it also absorbs and re-emits and behave like a black body. So problem because of that, for our enthusiasts who want to study the sun is, you cannot see inside the sun. Just like you cannot see inside the earth. You only see the surface of the earth, right? But we know there are many things happening inside earth. We know there is a core of earth. We know there is a mantle of earth. There is motions inside earth, tectonic motions inside earth. We know all this because of studying the waves, right? Like the waves on the surface of the earth, seismology studies. Similarly, we also use the waves to understand what is happening inside the sun. And there are some things like neutrinos which come out from all the way out. But mostly the information about inside the sun is based on the wave studies or the seismological studies, what we call. Of course, sun is connected with many other parts of science. People studying about cosmic rays, people studying about planet formation, planetary science, atomic molecular physics, plasma physics, or not. This gives a brief CV. You do not really focus too much, but remember a few things. Sun's mass is almost 3 lakh times Earth's mass, 3.3 lakh times. And radius is almost 100 times, 109 times, which means Sun is much more dense than Earth on average. Because you see the mass is 3 lakh times and Earth's radius is only 100 times. So Sun has to be very dense. When we say it is very dense, it at very high mass, it also means that the gravity is very high on the Sun. It is very difficult things to come out of the Sun compared to with respect to Earth. People have been studying the Sun for a long time, but very systematic study of the Sun started with Galileo Galilei around 400 years before. These are the real images drawn by Galileo with his hand. He focused his telescope onto the Sun, started drawing whatever he see on the Sun. And that is when he saw these pimples on the Sun god, which is very famous, as you all know, because at that time, Sun was sun god, right? Nobody could think that gods can have pimples. But Galileo told there are black marks on the Sun face, which keeps changing, growing. Sometimes it will become very ugly, it becomes very big, small. And people were very unhappy that sun god can have pimples, but do have. And they didn't know at that time why these black marks are. People thought these are burned out regions. But then they found that these regions sometimes disappear and that region become again bright again. So definitely it was not burned out region. It took almost 300 years after Galileo's observation. So Galileo started observing in 1600. After that, there was regular observation in different observatories around the world. But it took almost 300 years. Only in 1900s, we realize these dark sunspots are because of strong magnetic field. Of course, there was a reason that the Maxwell had to be bound to explain Maxwell's equation. The Zeeman had to be bound to explain the Zeeman splitting of lines, how the magnetic field and light thing. The Lorentz had to be bound and explain how the light and magnetic field interact. And then Hale made a polarimeter, because by then it was known that the light will change its polarization, there is Zeeman splitting, etc. And he started observing it, and he found that when he used his polarimeter, look at this dark spot, he realized that this is because of strong magnetic fields. And these dark regions are very big. Though in Galileo's drawing it looks small, if you keep an Earth here, you can see some of the size of those things are much bigger than Earth, in fact. These are naked eye objects. If you go to the beach and look at the sun surface, you will see these small things. Like now, if you go today, there are lots of sunspots on the sun. You can see them. I'll just show you that. The sun is also rotating, and you can see the dark spots. They keep rotating. There are different rotational speeds. The center part rotates faster because sun is not a rigid body. Sun is a fluid. So it moves in different speeds. We call it differential rotation. Okay. So this is an X-ray. I will come to that. So what happens is this magnetic field, because of this rotation as well as the buoyancy of the magnetic field, it starts rising because the pressure inside the magnetic field will be less, and they form these dark spots called as sunspots. That's a current understanding of how sunspots are formed and why you see all of them in pairs all the time. Because when you have such magnetic field rising, as you see in this cartoon, you always see that they will be in pairs all the time. And that is what is observed. Sunspot is mostly observed in pairs. Now, if you zoom in using bigger telescope, these are different photos taken with different telescopes. So if you change your telescope and start zooming in to these dark spots, which Galileo observed, you can see a dark spot here. Very small, tiny dot. So if you use different cameras and start zooming in, different telescopes and start zooming in, you start seeing this. You start seeing all these granulations around, and the dark spots become very interesting. And you can see there are some alien structures here, and inside also there are some structures. It becomes very interesting, actually. So these days, people study not this just like this. People also look at Like, for example, I do a lot of research on such things. Even my PhD students work on this. They all look at details of the small features. You see these hairy like features here, and you can even see if you zoom in further, there are some dark lines on these hairy like features. So these are all interaction of plasma with magnetic field. So it's very, very interesting to understand the physics of how plasma interact with magnetic field and why such features are formed when this interaction happens. This is some fundamental physics to understand what is all these features created when plasma and magnetic field interact, which is these things are very, 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 very difficult to create. I can say nearly impossible to create in the lab. And it is very difficult to create even on computer simulation because we have not understood the theory fully. Because you need astronomical scales to create such features. Then there is also a cycle for the sunspot formation on the sun. You saw earlier that Galileo's movie that there is a lot of sunspot being formed on the sun. Or even here you would have seen sunspot being formed on this. Now, if you start marking the sunspot, there is a cycle. If you ask the location of the sunspot, the latitude, this is the latitude is almost close to zero, right? So if you start looking at the latitude of the sunspot, so on this figure, on the top figure, this is the latitude of the sunspot. You can see equator, EQ it is written. 30N is the north side 30 degrees. 30S is the south side 30 degrees. And every day you start, or every month on an average, you mark where is the sunspot found and whichever sunspot is found. So you see that initially the sunspots were all in high latitude. You see 30 degree north and 30 degree north. If you take 1881 line as one exam starting point, you see that all of them are in high latitudes. And over many years, as the time goes, the sunspots start appearing in lower latitude, and it comes very close to equator. It doesn't touch the equator much, but they come to up to 88 degrees and all. And then they start forming. And by the time 1890 comes, you start seeing again sunspot on the other equator, again on the higher. And if you look at the number of sunspots, you see that this is forming a cyclic nature. You see here, as per when the sunspot was on the high latitudes, there were very few number. And when it came to almost 20 degree and all, the number of sunspot increased. This is the number of sunspot, average area. And start reducing. So this started showing a cycle. And now we know that it is a 11-year cycle. Every 11 years, the sunspot number increases, area increases and decreases, and it changes. And there's also a magnetic cycle of 22 years because there's a pole exchange. Something interesting happens in this thing, which Siddharth was telling me to talk about, which is very interesting actually, that people started looking at this historically. So there was a paper, science paper in 1976 or something, where he looked at the old papers, whoever reports about sunspot. So whatever you see, blue is basically from same one observatory, the Belgium Royal Observatory of Belgium, and these are from different observatories collected together. That is why they use different colors. But if you take the historical data, you see the cycle always happening, and this is an averaged curve, the black curve. You see that almost up to 1710, from 1650, 1640 to 1710, there was almost that is almost 50 years, or almost 28 years actually, this bottom. You see there is very, 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 very less sunspot. So in these 30 years, there was only some 50 sunspots altogether. Whereas if you take 30 years somewhere here, you will see like thousands of sunspots, 50,000 sunspots. So there was very less sunspots during this time. Nobody knows why it happened. So why this process or this dynamo got switched off during this time. It is not about recordical thing. People have verified it in multiple ways. One is people from the sunspot thing. There has been people in Europe who records this aurora borealis. Solar flare. I'll come to that in a moment. But just to give you an idea, there are people who keep record diary of aurora borealis seen. People have gone and studied this aurora borealis, and they find that during this time there was no aurora borealis recorded at all. So there are multiple sources to verify that there was a Maunder minimum when there was no sunspot at all. People have also looked at these ice cubes to see the the particles, you know that, right? The cosmic rays and all create some carbon thing in the ice cubes deep down. They dig and they can find, they analyze, and they can find out the solar activity. Like people, similar to carbon dating sort of thing. And that also have confirmed there was a sort of a minimum of almost 30 years or a longer minimum during the film. But what is interesting, more interesting part is there is a, first of all, we don't know why this minimum happened. And this is the main number itself, because there is actually the two couples, the Walter Maunder and his wife, Annie Maunder. The story goes that they together published papers, 2-3 papers on this minimum, and since his wife, the Annie, don't have a degree or she never went to college, that time Royal Society of the Royal Astronomical Society of UK, England, London, they didn't agree that she can be an author because she never went to college. But she has been observing this sky, and she found that there are no sunspots during, from the historical data records. This paper was in 1800s, not during that time, end of 1800s, 1890 or something like that. So just 100 years before, not very far away, just 100 years before, they didn't allow her to be an author of this publication because she never attended colleges. So her husband wrote all the papers, some 2 or 3 papers about this. So that's a Maunder thing. But later people recognized that it was his wife, Annie Maunder, who did a lot of studies on this, and people do accept. Now people say both of them together discovered. It's not really discovery, even there were papers before that about this, but they wrote a piece of paper which made it more popular sort of. So what is making it more interesting is actually, this is a painting of similar time, which is called Little Ice Age. This is a Thames River in London, and they used to conduct fest, like Habba we call, no, in Karnataka, on the top of Thames River. People, you can see this is on the Thames River. People run on the Thames River, they move. The bullock carts used to ride on the Thames River, they skate on the Thames River, because the whole Thames River became ice. It was totally frozen. This has happened multiple times, but this was a longer duration of winter. People call it sort of Little Ice Age during the similar time. And interestingly, this Maunder minimum and that Little Ice Age somehow matched. So the red curve, the CET means central temperature, inclement temperature, I think. This is northern hemisphere temperature, and NHT means. So people see that there is some matching between this Maunder minimum with this low temperature. But there is no scientific proof till now which says that these are connected. We really don't know how sunspot is connected to the climate. Of course, sun is connected to the climate, that we all know. Sun is connected to the climate because the sun is the one which drives our climate. But how sunspots are connected to climate, there is no clarity on that. Means ultraviolet rays from the sun, whether they influence the climate, is something hot topic of research which we have no clue about. But there is an observation of this sort of thing, but we don't know whether it is an anomaly of one-time thing or is it some connection. There has been a lot of studies on this. People are still working on that, but there is no clarity on that. Okay, my time is running out because I have to talk about Aditya. Before going to Aditya, I have to ask this question: do we need to really study the sun from space? Because a lot of discussion happens on that. Sun is something which we see all the time, but do we need to study the sun from space? Yes, because you don't see all the rays from the sun or any other astronomical source coming to Earth. There is very few, only radio and visible comes to Earth. Okay, what you see here is the y-axis is atmospheric opacity, means the amount of light which gets absorbed by the atmosphere or attenuated by the atmosphere. So you see that this is X-ray, gamma ray and all 100% attenuated. Nothing comes here. And whereas radio, almost everything comes here. There is no attenuation at all. That is why we use radio wave for all communication purpose. So if you want to study the sun in ultraviolet, for example, or X-ray or gamma ray, you have to go to the space. There is no other way. That brings the second question: do we need to study the sun really in this wavelength, ultraviolet, X-rays, gamma ray? Is it really required? Why don't you study the sun only in visible and radio and be happy with it? The problem is, unless you study this object in multi-wavelength, you don't get the full picture. There is very famous story of multiple, this elephant, which I say, I'll skip that because of lack of time. Many of you would have heard about this 100 times. So this is just a proof that the sun looks really different when you look from visible and ultraviolet. This is the image of the sun, not today's sun. This is some old sun. I'll just show you today's sun after this. After this end of the talk, I'm going to show you some tools to see the live sun. I'll come to that. Just be patient for another 20 minutes maybe. Then I'll show you some tools which you all can play around sitting at home to see the live sun. If somebody want to see the sun at midnight, you can see the sun at midnight. I'll show you how to do that. You just wait for end of this talk. So the sun, it looks really different. This is the sun invisible, what you see from a beach or whatever. Now, if you look at it in ultraviolet, the sun looks really different. You just see this. This was the sun what you generally see. So we understood the sun as like this, the dark spots, then there's a very quiet sun, etc. But when you look the sun in UV, ultraviolet, you put your spectacles, ultraviolet spectacles, suppose you have something, you go to the space as an astronaut or something, you wear an ultraviolet spectacle which allows only ultraviolet rays inside, you see the sun like this. In fact, you get this alpha filters these days. You can see from Earth also. You see a totally different sun if you use a alpha filter in your telescope. You can see that actually from ground as well. So, or even calcium filter. If you can put a calcium filter from ground, you can see a totally different sun like this with hairy structures and all. So you see a different sun when you see from visible and you in ultraviolet. That makes us again curious to know why it is. Now you take another wavelength. Wavelength is written here. You see these dark regions. We call it coronal holes. Again, we don't know where is it coming from or the real reason for that. And so the sun looks really different in different wavelengths. You see this sun looks really different in different wavelengths, which means we need to study the sun in all wavelengths. And the only way, if you want to, only way to study the sun in all wavelengths is to go to the space. There is no other way. Sun also emits something called solar flares. It causes a lot of energy release. Also, it throws out material to the space. Remember here for a moment, I told you earlier, the gravity of the sun is so huge, almost 3 lakh times more than Earth, because its mass is like that. And the chunk of plasma it is throwing out is as much as the size of Earth. Then when even to simply launch a rocket on Earth, it did so much energy, right? So imagine the amount of energy required to launch this chunk of plasma onto the space. And where did sun get that much energy, which happens regularly on the sun? This is a smaller one. This is one of the tiniest flares. There are very, very huge flares of CME sometimes, coronal mass ejections. Where does sun gets all this energy? That is another question of research. People are still researching how is this energy, where is this energy release coming from? What is happening? How is it getting so much energy to throw out so much matter into the space? This is a zoomed in image of that. Same, these are real images. And sun is the only star where you can get such images as of now with the current technology. And you can see some of the failed one falls back, in fact, because of the gravity. That was a small one. There was a big one called Big Daddy. This is 1945. This also, there is a lot of interesting story to tell because this happened during the World War. It created a lot of, the solar physics became very interesting after this event actually, because it caused a lot of disturbances during the World War for the communication, etc. Again, I don't want to digress much telling that story because it can go on for a month if I keep telling all those stories. So what happens is all this plasma which is being thrown out. Of course, you know, when it is being thrown out because of this blast, it will move everywhere in the heliosphere. Some of them which is directed towards us will come towards us. This is a cartoon to explain that. It comes and hits Earth. Luckily, we have a strong magnetic protection around us. Because of the magnetic field protection around us, things won't directly come and hit us. But the magnetic field stops it slightly and it gets redirected, all this plasma, because plasma cannot cross magnetic field easily. But that sometimes causes local reconnection, etc., and cause this aurora borealis, what we call the burning of atmosphere. If you go to Ireland or Norway or Scotland or little higher up Scotland or all those regions, you start seeing all the Nordic countries, you start seeing this aurora borealis, nice, beautiful burning of atmosphere. The atmosphere start burning in different colors, all beautiful colors. That's called aurora. I think most of you would have heard about that. That happens because of that. The biggest problem with all these things is our space assets. For a country like India, for high latitude countries, of course, it will affect, but for a country like the equatorial country like India, it may not be a big problem because of the magnetic field protection directly, but our space assets will seriously get affected. Our satellites, the aeroplanes which is going up, and our GPS which we all use, etc., etc. All the electronics up there, which is strategically important, communication, all these things get affected when this huge chunk of plasma with high energy protons and all comes and hits it. It can destroy the electronics. If there are astronauts over there, they can even get killed. If there are it's an electromagnetic disturbances. What all electromagnetic disturbances can do, it can do. So these are very old news. You can see 1882 when people didn't know anything about this. There was some news article which saying that there is a storm of electricity from somewhere, and all the telephone systems got disrupted. So that was the solar flare happening at that time. We know where is it coming from. At that time, they didn't know where is it coming from. So if we want to continuously monitor the sun now to study all these things, one problem here is we have nights, right? If I put a telescope here, I can study maybe 8 hours in a day, morning to evening. That too, if atmosphere is good, there is no cloud, it's all good. So one way is to study this is you go out of Earth to a place where without any shadow, no eclipse, and this point is a very suitable place called L1 point. So any two-body system, there is different point, Lagrangian points it's called, where the gravitational potential field lines become null or become very weak. Means when potential field line very weak means if you keep it in that region, it is very stable there. So if you can go to L1, it's nothing in between. There are Mercury and all in between, but they are very, very, very small. It won't cause any occultation, serious or no eclipse. You go out of Earth and Moon system and you go and stay here, you can see the sun 24 hours continuously and comparatively stable orbit as well. That is the idea of this Aditya L1 mission where we sent to the L1. And this is the image of the sun during eclipse. I think recently also there was an eclipse in American countries. Some of you might have seen the images, videos and all. But the problem is, another interesting fact is the same eclipse, you can see when eclipse comes, you start seeing corona, which is very beautiful, which is difficult to see without something occulting, this natural occulting of the moon around on the top of the sun. And this corona also itself, people find that this is very, very hot because you start seeing certain transitions which can happen only in million Kelvin degrees. That is very interesting because any object, as you know, if you have a candle or a bulb, as you go away from that source, temperature will go down. Here also initially temperature goes down. But at some point, temperature starts increasing because you start seeing when people, during eclipse, when you started looking at these regions, you start seeing X-rays getting emitted. How did the X-ray get emitted? If the temperature of the plasma is million Kelvin only, X-ray can get emitted. Or you start seeing, when invisible, you start seeing certain spectral signals, certain spectral transmissions like iron 39, 14, certain spectral transmissions, which is possible only if temperature is very high. So we know that this temperature is very high here, which is again a big question why we don't know temperature of the corona is very high. Another interesting thing is this eclipse, these are different eclipses of 4 different times, 4 different eclipses. The corona looks really different in all 4 cases. Sometimes it was well distributed, sometimes it was like a helmet streamer or look like a helmet, no? So this looks really different. Why it is different? It is definitely magnetic field, we know. So we would like to study this more. Problem is we have only 20 minutes of, this time 8 minutes of eclipse. So in your lifetime, you may see 2 or 3 or 4 eclipse, even if you go eclipse chasing. At the best, if you have seen a 4 or 5 eclipse, 8 minutes each, the whole time to study is you get is 20-30 minutes. You cannot study everything in this time. So we need artificial eclipses to be created. Artificial eclipse creation is very simple. You keep an occulter. It's very simple to say, but very difficult to make it. And because you can try it, you can keep a coin and see whether you can create an eclipse. You may create an eclipse, you may hide the sun, but you won't see the corona. because of scatter and other things. But technically it is possible. And that is why the idea of Aditya was born, that you want to create an artificial eclipse. We started with that. People have tried this earlier. This is an artificial eclipse created with LASCO on board SOHO, a NASA satellite. So you can see the sun is hidden with an occulter, and then you start seeing the background. And you see all these big blasts happening. You can see the background stars actually. Accidentally, you can see some comets coming and falling onto the sky during this process. So now we can observe all this. These people have been observing this from 1996 when SOHO was first launched. This beautiful images that is coming out. But we wanted to go a little more close by. It is very far away. Now, country is very big. That's why we decided we need Aditya. Aditya is a mission with 7 payloads. I will not go to the details of all these because I'm already 4 o'clock. But I'll just give a brief. Maybe if you are interested, we can discuss it after the talk in the question and answer session. I think most of you would have seen all this. We are already in this L1 orbit, and there are 7 payloads. There is a VLC. There is a ultraviolet imaging telescope. There are 2 X-ray instruments, and there are some in situ instruments for measuring the plasma properties and magnetic field at L1. This is image of the satellite. This is how the VLC will see it. And this is suit which I closely work with, so I have a lot of interest in this, which is an ultraviolet imaging telescope. You already saw some photos of ultraviolet images. This will give you near ultraviolet images, basically covering the photosphere to chromosphere. Again, I'll not go to the details of this, but unless any of you are interested specifically about this. So this will give you this region, photosphere to chromosphere, and how much ultraviolet rays coming from the sun. Ultraviolet rays are very special because they get absorbed by our atmosphere, and that influence, as I told you earlier, we don't know how sunspot is connected with our climate. If you want to solve that puzzle, the key or the secret is in ultraviolet, because the difference of a Maunder minimum to current is the amount of ultraviolet rays coming from the sun. That is a major difference. Ultraviolet, of course, X-rays, gamma rays are also changing, but they are not the one which interact with our atmosphere. But we know that ultraviolet rays interact with our atmosphere. Atmosphere absorb all the ultraviolet rays, and it heats up our atmosphere, that we know, upper atmosphere. But so, is there any secret of this ultraviolet rays connected with climate is something which we don't know. So people still research on that. Okay, this is how the telescope looks like. Okay, I'll just skip. Okay, this is a telescope, actual telescope being made in the lab. And this is, I'll just show you some photos of our telescope being delivered. It's packed in a very nice container. And it's sitting on the top of the satellite. I think most of you have seen. These are all the photos in public. They're already available. This one is a VLC, and this one next to that is a suit. This is a big Aditya satellite. To get an idea, you look at this chair. It may look very small, but you look at this chair. Size of the satellite you will get from the size of the chair here. So big, in fact, because if you stand here, you may reach only up to here. The size is so big. And this is on the top of the rocket. Looks very small again, but you look at this person standing here, people standing here, then you will get an idea. It's on the rocket tip before the heat shield closure. This is a PSLV stage 4, which you see here. Again, this is available in public platform ISRO web page. This is just before the launch, the group photo. And this is the launch. I think all of you would have seen the launch. And this is the suit door opening. There's a camera which you can see the door getting opened. And we did multiple times opening, closing. Even now, there are some tests going on. And this happened on 5th December 2023. And we took some nice images of the sun using this. You might have seen this again in media, different UV images of the sun. This is just one example. And we have seen some nice, so you can see some nice coronal mass ejection happening here on this. This is observed using suit. And we have also observed these active regions. You can see some nice flares and all happening here. In fact, I'll just show you now. You can even go every day to see the suit images. You can see this is an image from April, 20 April. Right now, suit is switched off because we are doing something called baking. But till 24th April, it was on. And you can see everyday movie like this from the Suit webpage. Just the full movie or ISRO webpage, you can go and see these images, just the movie of this, how the sun looks every day. Okay. And also this Aditya has some X-ray telescope because people are interested to study the X-ray coming from the sun. Again, I'll not go to the detail. It covers the X-ray region, which is soft X-ray to high X-ray. These blocks are marking that. I will discuss this if anybody is specifically interested. I will not go to that in detail. Okay. In summary, there are some lot of unanswered questions, and Aditya, well, when this is the right time for all the young people to enter into solar physics research. So before I end, I just would like to show you something more. If I have 5 minutes, Priya, can I just take 5 more minutes?
Yes, sir. Finish it up.
Yeah, I wanted to show you if you can see my screen. Can you see my screen?
Yes, sir.
Okay, I just want to show you how the sun to see today. So if you can, there are multiple options. You can go to this site called, you can just Google search SDO sun today. You can just search this SDO sun now, if you can see my screen. And the first link which comes, you can click. That gives the Solar Dynamic Observatory sun now. So you can see this is today's sun. So the images which I showed, I took from here. So if you just click on this, it shows the sun right now. So you can see the timing here. 4 May 2024, 10:16 UT. 10:16 UT is 10 plus 5, right? So that is 3:45, 3:46, 3:47. So we are just 4 o'clock now. So this is the sun 10 minutes before. The image taken 10 minutes before. So you can see the most recent images from here. So if you want to see the sun which you see on a beach, you can go here, you can just see this. You can see lots of sunspot. You can verify this. If anybody doubt this, go to a beach today or climb your terrace in the evening. And if your sky is clear, where the place where I'm sitting, the coastal west coast, the sky is very clear. So maybe if you go to beach, the Malpe beach nearby or wherever you are, if you go to terrace and look at the sun, you will see the sunspot. This image was taken 3:45, yeah, just no 10:45, 9:45, so half an hour before. So you can see there is a sunspot here, there is a sunspot group here. If you want to see the corresponding magnetic field, you can see wherever magnetic field, wherever sunspot was there, you see all these bright things. As I told you, if I want to see how the features, you see all these features, wherever sunspot is there, it was very bright. You can play around with that if you want to see the sun now. There's another tool, you can type helioviewer.org, which is my very favorite, and I think many of my students also. Every day, they all spend time playing around with this. You can open this HelioViewer and you can choose this different wavelength by here. So this is the image, the sun now. Let me click newest. So yeah, 9:51. You can see the time here, which means 10 o'clock UT, which is around 3:30 UT. It's loading. So this is just half an hour before the sun. Now, if you want to see how the sun look in magnetic field, you can slightly move this slider here, and you can increase opacity, and you can just see. You see how the visible sun and magnetic field looks like. Wherever sunspot is there, you can see there is strong magnetic field. Now, if you want to see how the UV 171 looks like, you see this. So you can see this is just exactly on top of sunspot, right? So it's very beautiful. If you just sit with this, you will not. If you are bored at some point, just open this and just watch this. You will not get bored for long time. Because something you can simply play around with. I do that many times. Even if you are not interested in solar physics, you can. This is a tool which you can play and do any time. Even night 3 o'clock, night 1 o'clock, you are full. You are not getting sleep. You want to see how the sun looks like now. You can just open HelioViewer and start playing around this. You can add more wavelengths. You can add many other things and see this. Okay. In Suit also, there is a Suit webpage where you can go and also get the Suit observations of not the data, but the sun today sort of thing, image of the movie of the sun of that day, you can get from there. That's all from me. Thank you. If there are any questions, I'm open to answer.
Thank you very much, sir. Very interesting. Okay, I'm unmuting everyone. If any questions or queries, you can open to ask. Okay, Venkat, go ahead.
Am I audible?
Yes, yes.
Okay, so sir, you talked. This talk was mostly about sunspots, but in a way, they can somewhat be related to a more more type of coronal mass injection or the solar flares. How how do you think that we can use sunspots to track these events, and then how we can end up protecting ourselves from such a massive type of solar?
Yes, so as I showed you that movie earlier, most of the solar flares are connected with sunspots. Sunspots are the display of strong magnetic field. And we know that flares are connected with sunspot. It depends on the complexity of the magnetic field, etc. So most of the solar flares, I showed you some movies of coronal mass ejections and solar flares. They're all connected with, mostly they're connected with sunspot. Of course, there are some solar flares not connected with sunspot, like prominence flare, etc. But most of the flares are connected with sunspot. So if you want to protect your space assets, there is something called space weather studies. People study how the space weather changes. One way is to observe the sunspots and the magnetic properties of the sunspot. That is how the flare prediction people are trying. We are still not successful in predicting the flare. We don't know when exactly a flare will happen, but we are quite good at knowing that this particular sunspot group will flare. So we should be careful. So there are enough protections. We can switch off the satellite. We can do many things to protect it from all these things.
Right,
But
sir.
it's still an open problem. We cannot predict it fully, but there are attempts to do that.
Okay, sir. Thank you, sir.
Okay. So questions in chat box, I think.
Okay. Please share the link of tools mentioned. Okay, I'll do that. Are sunspots available all the time? No. So it depends on the solar cycle. I talked about the solar cycle, right? So solar maximum time there will be a lot of sunspots. Solar minimum time there will be very few sunspots. So these days, you will see sunspots all the time if you are looking now. But after a few years, that number will be very less. So if you are asking about nowadays, most of the times there will be sunspot, but I'm not saying all the days. There are days without sunspots also. But if you want to just look through the telescope, please do. You will see a sunspot definitely these days. But don't look directly through the telescope. Your eye can get burned. You know, sun is very dangerous. Either use proper filters or you project the sun onto a wall or some screen. Never try to look the sun through telescope. And there is a saying that we used to say that you can see the sun directly through telescope only 2 times in your life. One through right eye and one through left eye. So don't try that.
Okay, one more question, sir.
Is Maunder minimum periodical? That is a very $1,000,000 question because we have observed it only once. There was something called Dalton minimum, which is very small one. We don't know whether somebody observed for 10,000s of years, whether it will come again and again. That is something which we don't know. Because our lifetime, we started observing only 400 years. It has not repeated in 400 years much. There was some prediction that it will come again soon, but the sun has not shown that. Even the theoretical studies, the dynamo theories, what they say, they are very successful in predicting the 11-year cycle. They could theoretically say why this 11-year cycle happens on the sun. But even those theories is unable to predict this long switch off, why this long switch off happens. So the answer is we don't know whether Mount Abu is periodical or not. It may be, it may not be. We don't know. We have no idea about that.
Srijit Srinath here. It was a fantastic talk. Maybe at the concluding remark, you can tell the institutes in India and abroad, which are mainly working in solar physics, so that students can make a choice in their
Okay.
future.
Okay, these days solar physics has become quite popular. Once upon a time, it was very little popular. Reason is when we were observing from ground, it was repeatedly the same sun I was saying. But after the launch of satellites from 1990s onwards, like 3 decades, when people started observing the sun in ultraviolet, X-ray and all, it become the whole story it's a revolutionized the way people understand the sun. So it has become quite popular, and there are lots of places these days in the world which study the sun. So listing out the whole global thing will be very difficult. I can quickly say in India, there are many places. If you take from south, in IISER Trivandrum, there is some people working on solar physics. IIST, there is some people working on solar physics. I am in Manipal, which is sort of on the coastal area, Udupi, in the Udupi town. We have a solar physics group here. Then Ooty, there is a solar physics group connected to the Ooty Radio Telescope and some part in Madurai and all. Then Kodaikanal, we have Kodaikanal Observatory, which is the oldest observatory in India, which has produced very interesting science. It is 100-year-old, more than 100, 125-year-olds. Actually, next year, the 125th year celebration is coming up of the Kodaikanal Observatory. And then in the Institute of Astrophysics, Bangalore, there are many centers in Bangalore. The Raman Research Institute, Indian Institute of Astrophysics. Then Gauri Bidnoor, there is a radio observatory which do a lot of study of the sun in radio, continuously monitoring the activities on the sun. Then coming up, midway there is a lot of them. Pune, there is Ayuka Pune. Then Pune University also there is something. IISER, all the IISERs, somebody or other, all the IITs. Many people, there is solar physics research happening now. And PRL, Ahmedabad, there is a research group. There is a Udaipur Solar Observatory in the mid of Udaipur Lake. It's a very 50-centimeter telescope, which is very nice place. If you are going for a tour to any time to Rajasthan, Jaipur or Udaipur, please visit Udaipur Solar Observatory. It's a very beautiful place. Then Kolkata, there is IISER Kolkata. I told you, most of the IISER these days, some solar physics people are there. Most of the IITs, there is somebody working. So I'm not listing it again. Then there is Aryabhatta and the Aries in Nainital. Again, if you are going to Nainital for a tour or something, please visit Aries Nainital. There is a very active solar group there in Aries Nainital now. Then, yeah, I don't know. I missed any place. Srinath, you can add in if I missed any place. And different ISRO centers, of course. I don't know to list it out separately. Bangalore and SAC Ahmedabad, and there is a lot of people studying the sun in different ways. ISRO's major interest may be solar, space weather and all, but Bangalore, there is a space astronomy group which do a lot of studies in sunspots and X-ray, especially soft X-ray. So the 2 X-ray payloads on Aditya were built by the space astronomy group, where myself was a alumnus once upon a time. And maybe, I don't know, I missed any place. I'm just thinking from my mind and telling.
Is Mount Abu and Hanley also doing some solar physics? I don't think.
Not really. Hanley, there is no solar observation, and Mount Abu also there is no solar observation. There is a new solar telescope being proposed at Meerut, which is in the near to Hanley, little more ahead of Hanley. In Meerut, in fact, IAEA has procured some land, and there is already a telescope there, which is basically for the site study. But there is a proposal to keep a big observatory there. But in Hanley and Mount Abu, there is no solar observations.
Is Growth Telescope doing some solar observation?
Growth, I don't think Growth is doing solar. They look at extra
Celestial.
things. Yeah. They're all nighttime.
Yeah, that's a fair list of institutes.
Yeah.
Thank you.
Any more
Actually,
questions?
that April 1st week, IAEA celebrated 125th year. So this is 125th year of Kodai Observatory. Yeah, thank you, Girish.
Any more questions?
Now, Girish, if you want to add anything, you can add. You can ask, madam.
Yes, Girish, sir.
Nothing from my side. Thank you, Srijit, for a wonderful talk. So we have covered almost everything. Just tell me when you are going to make your data public.
You should tell.
Whether Girish should answer or Srinath should answer.
Girish should answer that question. Okay,
We'll keep-
generally saying Aditya data, actually, no, just because he's told, the jokes apart. Right now, what happens is some testing is going on. Any satellite after we launch, we need to do certain testing after going there because of the rocket taking it up there and many changes happens. In ISRO terms, they call it performance verification. So
TV face.
yeah, so right now those performance verifications are happening. You can see that, as I told you earlier, since we have these daily images of suit image, you can actually go there and maybe I can quickly, I don't know whether I have 5 minutes to show that. People can see that these performance verification minute tests are happening because of that. Sun may be jumping up and down, moving apart, etc., etc. There is some, they had somewhere in the site some daily movies for a public outreach purpose was putting. Maybe I'll find it out. Exactly, I don't remember where it is. I showed one in my screen.
No, it's not yet started even in IUCA website. Maybe because it is not allowed for public daily images.
Yeah, yeah.
Of course, data is being under the PV phase and it is getting back to ISSDC. A decision has to be taken to make it daily image in public very
Yeah.
soon.
Yeah.
One more question, sir. One question in chat box, sir.
You have again coronagraph idea to observe the sun. Is it Aditya project? Is the no, not really. Coronagraph has been made for quite a long time on ground because it is something which strikes your mind immediately, right? You put a coin and block the sun. So there are ground-based coronagraph for quite a long time, multiple coronagraphs. But ground, the problem is our atmosphere is having a lot of scattering, so very difficult to see the corona properly with ground telescope. Means you need a bigger occulter, etc. Even space, this is not the first one. I showed you the images, movies of Soho, which was launched in 1996, and they have produced last 10 years from up to 2010, 2012, lots of images. But that also, the occulter is much bigger than the sun. So Aditya was, the idea was that we should go a little more close to the sun. We see the inner corona, what we call, and try to capture that. That was the idea of VLC on board Aditya. It is not the first one, but it was a unique one globally that way.
Srijit, if Venkat is alive, Venkat, are you alive? Line? Yeah, Venkat, you are there. He is a very young, what you call space scientist who is not going to school, but he has published already 4 or 5 research papers. He is doing a lot of work on space science and technology. Just to introduce you, the first person who asked you the question regarding solar flares and CME.
Okay.
I mean, maybe if sometime he gets, I would ask Venkat to keep in touch with Srijit, and he writes a lot of programs, he's good at software, many things. He is maybe 5th or 7th around that type of school, but he's not going to physical schools.
Okay.
When he's a
Please get in touch, Venkat. My email was given in my presentation. Please write.
Yeah. Venkat, are you there? You can say hello. Madam, it's officially closure. People can have informally based on the time of Srijit.
Okay, sir. I think we are already 20 minutes forward. Okay. We wind up here, sir. I think no more questions from audience. Any questions, sir? Vasudevan, sir? Anything to ask?
I think, madam, you can formally
Yes, sir.
conclude
Yes,
it.
sir. Okay, thank you, Srijit sir, for wonderful. Vasudevan sir, you want to ask any questions?
Yeah,
Question in the ಏನಾದ್ರು
I don't
ಕೇಳೋದಿದ್ಯಾ?
have.
Okay, okay, sir.
No. Thank
Okay,
you.
sir. Thank you. Sir, your guidance has deepened our understanding of the sun's mystery. We are truly valuable, the invaluable contribution to today's session. Thank you very much, sir, for accepting and for being with us. Thank you, one and all, for being with us.